All right. Hi, I'm David. I'm the CEO for BioBeats, and we're a machine learning company, but we look at well-being from emotion classification first, and then we do physiology classification of different sorts. I started this company a few years back, primarily as a result of research I did as a result of dying at Brussels airport. And what I mean by that is that I had a cardiovascular event at Brussels airport where I was put into an ambulance and my heart stopped and they brought me back with paddles. But unfortunately, their system had already reported a dead code to the arrival team. So when I showed up, because it turns out loads of people died at Brussels airport, they'd already started forensic paperwork, which is kind of, and then when I arrived, the nurse said, here's your toe tag and your paperwork and stuff, and it should tell you got to do something about that, right? Like whatever it is that you're doing isn't working. And I was an AI researcher, and I used neural networks to make music that imitated human improvisation. Like how do you know which note a jazz musician is going to play next? And so I used predictive modeling and neural networks to look at the next note. It's kind of what I was interested in. So I thought I could model human biology systems that could tell me, how to save other people from dying, from stress. The problem is stress is really not well defined, right? There's no golden standard for stress. You can detect for diabetes and many other conditions, but stress is really not one thing. It's a 90s term. It's really an umbrella term. It's about lifestyle. And it's really a reaction to challenge. The adrenal pituitary axis is designed for fight or flight. Should you run away from the bear or should you try and scare the bear? I mean, it's not designed for office work, right? We're not really that old evolutionarily speaking, right? So what the problem is detecting not stress, but good from bad stress. That's really, arousal versus valence, right? And detecting arousal versus valence at the machine learning level, we thought it was going to be really simple. It's like, oh, well, let's try EEG. And then it turned out, of course, that portable EEG wearables are still in the sort of Star Trek era, and they make everyone look like dorks and don't work and don't give you high fidelity data. And it's really not, it wasn't going to happen, so we looked at cardiovascular instead. What we were trying to figure out is, how do you detect prolonged stress without recovery? How do you figure out whether people are recovering quickly enough from stress in daily life? So we started to look at the physiology of stress, and that meant looking at the autonomic nervous system from the sympathetic, so fight or flight, like getting into sort of must fight kind of sympathetic mode, or parasympathetic, where people are just resting and digesting and generally okay. The problem with sympathetic versus parasympathetic activation is that the only way to really look at it is from heart rate variability. And until very recently, with wearables that can give us intervals between heartbeats as a data point, it was really impossible to do on a continuous basis. You could go into a clinical psychology lab and rig people with electrodes and get proper R intervals, but you couldn't really do it in the wild. So what I wanted was to measure HRV to estimate autonomic balance, and then to find a way to teach people a habit that could break the cycle between parasympathetic and sympathetic autonomic response. So we knew from every nurse in the NHS ever that they get taught how to teach people Pep Boys breathing when they're in shock or in pain. Right? So like breathe in 5 seconds, breathe out 5 seconds, do it from the belly. That means that from the belly and the diaphragm pushes on the vagus nerve. The vagus nerve releases oxytocin. Oxytocin kills adrenaline. Job done, right? So they teach that to people who are either in shock or pain. And we thought, well, in the States at Harvard, Herbert Benson pioneered an entire decade of studies on vagal response, and looked at the biology of this. So we thought, okay, fine. We've looked at EEG. We've looked at several parts of this in research in the States and in the UK. And then at that point, I wanted to just go forward. And I gathered a whole bunch of cardiovascular data from people in the wild. But instead of looking at getting thousands of people into a lab, we looked at how to model HRV and stress from differences between users, using the intervention itself as the point in the middle. So ask the person how they feel, use the intervention as the actual data, and then ask them how they feel again. We needed context. We needed to gather passive 24/7 instead of notification-based models. in order to then train machine learning-based interventions that could say, okay, your sympathovagal balance is declining. You're diving. You're not there yet, but in a day or so, you're going to either have a panic attack or a heart attack or a very serious wobble. So we looked at circadian rhythm from that sort of data from scale, and then wrote an application that made music out of your heart rate by looking at the heart rate from the camera on an iPhone, lighting up the LED. We knew it could be done. Azumio had done it before us. So we just figured out a way to light up the camera, take as many samples per second, as many frames per second of the finger. We did a fast Fourier transform of the color red. Turns out you can get a heart rate from that. So we got heart rate from that, and then we got heart rate variability from the periods between heart rates. It turned out that actually the iPhone camera, even at the 4 and the initial models of the 5, you could get high enough sampling rate to get really good HRV. So we published during South by Southwest. We told the Austin Art Museum, we told people queuing up for a Flying Lotus set at the Austin Art Museum that they were going to see like biometrics, life, and whatever, and they all downloaded our app, and then it went kind of viral, and then we got 100,000 users to download it and use it. It turns out that that's possibly the largest cardiovascular HRV database ever compiled. Right? So we thought, okay, yay, right? And we have data to learn from. And we built, at the SDK level, a bunch of data acquisition and pre-processing functions that then pushed it to the cloud on an API. Then we built a machine learning engine around. The aggregate data for which told us that we were approaching several things the wrong way, such as if you're going to gather HRV, and even if you look at ultra-short measurements of HRV, like high frequency, low frequency, or RMSSD, which people use in fighter pilot planes, they shine a strobe light and they measure RMSSD from pupillary recovery to see if the pilot is still able to recover from stress. Otherwise, they shut the weapon systems down and stuff like that. Because you don't want somebody who can't control their stress anymore firing at will. So, and then we started building dashboards that showed people what we could see at our end to see if biofeedback from seeing their own data changed that reaction. At the dashboard level, what we wanted to do is not to concentrate on fitness or sleep efficiency or anything like that. We wanted to start with stress and then levels of activity, correlation between activity and stress, correlation between sleep and stress, etc. And then we wrote a series of other applications like Get On Up, which was just an app that made music out of accelerometry and movement and encouraged people to go and go for a walk. And that taught us a little bit about user habits and behavior change and when to intervene and when to say something. Then we figured out that actually, as well as a machine learning company, we were an AI company that needed to understand human behavior from the point of view of not being desperately annoying when you try and help somebody, right? And the point about that was, when is the right time to go for a walk? Well, if you're about to attend a board meeting, clearly telling you go for a walk is a useless piece of advice, extremely annoying, and will get our app deleted right away, right? If not the phone thrown at the wall. Incidentally, when I first started this research in the NHS in Stoke-on-Trent, I had loads of patients using Android phones and live reporting on blood pressure data. These were oncology patients, critically ill, terminally ill with cancer. And one of them, the signal kept going off and triggering a whole bunch of nurses to come to their home. And it turned out, of course, that he was throwing a 600-pound Android phone at the wall every time he opened my app, which taught me more about UX design than anything I could have learned at university, I reckon. So then we wrote Here and Now, which is an app that tries to teach the Pep Boys technique live, right? People in the iTunes store seem to like it. It got featured a couple of times in Austria and Germany. We're big in Germany, yay. And then in other countries and so on. And suddenly we had around 12,000 people using the app on almost a daily basis. And we started to learn very differently, both about user behavior and sympathetic versus parasympathetic activity. Then suddenly insurance companies got really interested in us because they were thinking about their business models changing from claims-based insurance to preventative health. And one way to look at preventative health was to look at productivity and stress and fatigue and recovery and burnout of whole cohorts of individuals in a workplace. So we were asked to analyze a whole cohort of individuals in a workplace in London. And what we thought was, okay, fine, let's build real-time data from wearables and smartphone sensors. Let's look at the typical accelerometer, gyroscope, location, heart rate, etc. Then let's do a whole bunch of shallow learning, right? Bayesian models of just classifying the activity at large. And then let's train a few recurrent neural networks that can give us at least the basis for understanding for behavior patterns. and we'll look at HRV and stress, and that correlation is the primary focus of what we do. What we were looking for was deviation from habit, the possibility of intervening as a proposal, and the correlation of real-time data from wearables to the physiology patterns we could see at the Bayesian level. So essentially, we had deep learning models being fed by Bayesian models that we already knew worked at the 100,000 people level. So then we ran out of bandwidth, we ran out of computational power, and as anyone who succeeds in deep learning, we just ran out of processing, right? We ran out of compute. And so we started to look at a cycle where we would build machine learning models in the phone itself, then push the model to the cloud, and then compare that model to every single model we'd ever seen before, refine the model, and push it back to the phone. Turned out that cycle is really, really efficient, and that actually there are enough cellular data packets in a typical urban environment. It doesn't work in Nebraska, it turns out, where you can cycle that model a lot, right, and iterate on it. But there are a few conceptual challenges. As I said before, stress is really loosely defined. Right? We can see parasympathetic activity in a person, and then suddenly huge swathes of sympathetic activity coming into the body, and we can look at that, but it could be any number of things. From HRV, we can also tell inflammation, and sometimes it's not at all stress, it's good stress. Perhaps they're snogging someone, or they're running for a bus, or they're getting mugged, and we have no way to tell which one it is, right? So context is paramount, and without that context, we can't really associate what we do at the machine learning level with any kind of usefulness to the individual. The variables for this, the latent variables for this are physiological, psychological, and then personalized. The problem is you can't personalize without both the psychological and the physiological. So that meant we had to learn how to ask pertinent questions from scales that the clinical psychology literature understood, that had validity at the ontological level, in order for our machine learning models to understand how not to break people's hearts, basically, right? Because the last thing you want to do is to tell somebody, everything about you right now tells me that you're at the very cusp of the onset of depression. Thank you, right? It's like, well, that's useless information because you haven't told me why or how or like what I could do to solve it or whatever. Also redundant information, because surely if you've downloaded an app that could tell you that, you already know that something's wrong, right? But more importantly, because people interacting with AI is a really fragile relationship. The problem is, if you're us and you start to see the problem, right? Once we had a whole bunch of people in our database whose movement we were tracking and looked wonky, and we thought we made a mistake. They all looked like they were leaning to the left, to the right. They were all leaning to the right. And we couldn't figure out what it was. And we just asked a GP with more than 40 years of clinical practice, like, what would make you think, what would you think if you saw somebody leaning to the right? I said, oh, that's Parkinson's. And so we checked several times. It's like, what do you mean? It's like, oh, I've seen that several times. So like people walking out of my practice, and I've had them walk back in and go through some tests, because I know that the way they lean, that sort of special kind of lilting lean, it means the onset of Parkinson's. But because of the ethical boundary between us and how we collected the data in the first place, we couldn't reach out to those people and say, hey, by the way, you have Parkinson's, right? So we were at a completely impossible ethical boundary between us, the data, and the 47 people in our database who probably have Parkinson's. The problem about this is twofold. There's the algorithm problem, like what does the algorithm do with information it doesn't know what to do with at the ethical level? The solution for which is don't be human, right? Because if you try to be human as an algorithm that has that much information about someone, you will fail, because humans would fail. How would you tell your best friend that they have Parkinson's? You'd suck at it, right? It doesn't matter what you try, you would suck at it. There's no good way to tell somebody they have Parkinson's, right? So it's not a problem you can solve. So having an algorithm try to solve it is stupid. The solution for the human is that we can't expect AI to solve the human condition, right? Or to threaten it. They don't. It's kind of an impossible thing to do. But here's the thing. The fact that it's an impossible thing to do is an interesting problem for AI. What does it mean, right? I'm hugely concerned with the impact of technology and its implications on activities of daily life, which is, after all, the bedrock that generates all the data we use in machine learning, at least what we do. Beyond this, I'm concerned with what this impact can tell us about our relationship to technology at large and how it could be useful. How can it help us cope with the mental stress of getting old, of forgetting which bus we take home or our wives' names? Right? It's a difficult thing to forget because the realization alone that you've forgotten is hugely stressful. So can it help us, cope with? Can it help us cope with the absence of information? The detection of disease because of a change in behavior is not enough. An algorithm that can detect that is a dangerous algorithm. It has a little bit of information, and a little bit of knowledge is a very dangerous thing. To answer the question, you got to look at philosophy, not ethics. You got to go back. In the same way that Bayesian models are the precursor to deep learning, philosophy is the precursor to an ethical problem in algorithmic science, right? If you don't solve the philosophical problem, you cannot solve the ethical problem. This is Bernard Stiegler. He was a bank robber, he was done for armed robbery in France and went to a prison in the south of France. And in prison, because he had time, right? He did an undergraduate degree in philosophy and then a doctorate in philosophy with a man called Gérard Granel, who wrote a theory called the large now. It's an awesome theory, and if you design algorithms, you should look at it. Because it teaches you how to be, how to look for long sequences of correlation. This guy in prison wrote a theory called Techniques in Time. And he's now running the Centre Pompidou in Paris. Like the foremost cultural institution in France is being run by an armed robber or a former bank robber, which is just awesome. Now, this guy, right, gave a breakdown of our relationship with technology, which I find really interesting, which I think should inform our work in deep learning. And here's why. You can arrive at an ethical perspective only if you understand that until man, only two systems of memory existed. Right? You had the individual memory of beings, and then you had everything else. But the nervous system of those individuals and DNA can't communicate. Therefore, that individual experience just can't be passed on. When that individual dies, so does their entire experience. So in sharp contrast, as soon as techniques appear, as soon as technology appears, there's a different idea. Information can be transmitted. You can talk about tools, and from then on, you can look at vast swathes of memory coming into the world that are transmissible from generation to generation, like camera phones or recording devices, the internet. All of those are nothing but like the latest avatars, right, of a system which began with the first carved flint, surely. Right? So now, this system is what appears to us as culture, right? And an algorithm should be informed in the same way. Like, what can you see? How are you historically informed? So what you use today, your iPods, your phones, and whatever, in 1,000 years from now, somebody will look at anthropologically. This is the origin, fire, right? So Bernard Stiegler basically says, we suck at being human because humans got fire from Epimetheus, the dumb brother of Prometheus, who had foresight. And Prometheus felt bad for Epimetheus, who got given the job by Zeus to give every living creature a skill, right? But when he came to human beings, he'd run out of skills in the basket, and he thought, oh shit, I fucked it up. So he went back into Olympus and stole fire from Hephaestus and then gave it to us, and we made nuclear bombs out of it, right? So that's the basic problem, is that in order to understand how to be useful to a human, you need to understand that humans are inherently messed up. The second problem is fear. The concept of techniques, right, is interesting from a philosophical standpoint. But what it points at is this relationship between genetics at the encoding level, epigenetics at the point where we know that there's an encoding system and we can track it, and then epiphylogenetics, this conversation we're having right now. Right, where we talk about the fact that we can encode the thing that made us. Now, knowing this, knowing at the anthropological level that this is true, that we're epiphylogenetically related, and that we could talk about it that way, means that you could look at a human being and say, okay, Sixlaff-Sinsentmiai at the University of Chicago in the 70s was properly true. There is such a thing as flow. If you put a human being with the right skill set and you give it the right challenge, they will kind of go into a trance. What's interesting is that in game design, that's already an understood thing, right? Machine learning algorithms in game design are already pathologically obsessed with flow. They want to understand how close the player is about to rage quit, right? How close are they to not playing the game anymore? Right? That's what machine learning in gaming is concerned with primarily. So when they look at pathways between a hardcore gamer and a novice gamer, they have all these structures and pathways on how to navigate from flow to fear to fire, right? To the condition that an inherent human being, that a human being inherently inhabits, which is, kind of messing around with fire and fear, to going into flow. And then they train neural network models from emotion classification. And it turns out that fast forwarding this, you can come up with a biometric model of activation of stress markers based on stuff that the gaming industry has done for years, but using real-time data that looks at valence and arousal as a way to look for the onset of disease, including the onset of depression. Now, when we knew that we could understand the onset of Parkinson's from that level, as sort of behavior at the rough, almost basic level, we also understood that this machine learning understanding could be a good basis for adaptive algorithms that understand that flexible nature of the data and that understand that galvanic skin response in HRV could, as a model of arousal and valence, look at preventative health causes, right? They could say, this looks like inflammation, but it also looks like the very onset of panic. Let's figure out which it is before we open our mouths as algorithms, right? Maybe if it's inflammation, it's not BioBeats' job anymore. Maybe it's Babylon's job. And so you have two AIs talking to each other, one handing over, when that algorithm knows that if they open their mouth now, they're going to say something stupid, right? Here's the problem, right? If you look at energy-based recurring neural networks, right? Anything like a Boltzmann machine, fed by recurrent neural networks. You could, and we've tried, find them a good way to understand human behavior from sensor data in order to tell whether the patterns overall indicate progression towards concentric, depressive behavior. And then to walk backwards in time in the data and fire behavior change opportunities at the user before their brain becomes used to depressive pathways in the first place, right? So before it takes hold. But recurrent neural networks and Boltzmann machines in general, or any energy-based model for density estimation of temporal sequences on the whole, where the feature vector and any of the time steps can be high dimensional and often is, it allows us to describe multimodal conditional distributions. But essentially what it allows us to look at is the sequence of history at any point in a given time. So we can look at all this stuff that happened between parasympathetic and sympathetic, like a bad meeting at 2 a.m., a panic attack at 3, or some kind of really chilled out moment at 5 p.m. when they finally got a pint in and are talking to a friend they know, right? We've seen that in stockbrokers, although it's more like 10 pints, but you know what I mean. It's kind of, and 9 p.m. instead of 5 p.m., but still, right? So they, there's like stress, alcohol, cocaine, Valium, sleep, right? And it looks like a parasympathetic nightmare. There's no parasympathetic activity. They're essentially superhuman. So how do you use a Boltzmann machine to look at that, to encode that? You could look at each parameter in the history and say, all right, well, they all depend on the output of a deterministic recurring neural network. It has hidden units. We don't know what's in there. But the single layer RNN is defined by the resulting model. And that model unrolls in time, right? It works in time, just like we do. So in the figure that you can see, the overall probability distribution is given by the sum of all these time steps in a given sequence. And that sequence can be heart rate variability events. They can be galvanic skin response events, where the right-hand side, the multiplicand, is the marginalized probability of the recurrent Boltzmann machine. The problem is, it's obvious. It's obvious. Why wouldn't you use recurrent neural networks to map when somebody feels bad? It's obvious. You just map whenever they dip and whenever they're going into sympathetic mode, and then you map that in time. If it gets more often, then you know that they're going to dive. So it's not a good way to spot the onset of clinical depression, because the onset of clinical depression, and Babylon, I'm sure, can tell you, and others like Ginger.io in the States can tell you, is more complex than what we can see at the deep learning level. And it certainly is like an advent moment right now where we can start to see those patterns at an epidemiological level, where we can have that sort of data. But it's primitive, it's early, right? It's exactly what Stigler talks about. It's epiphylogenetically flawed. It still sucks. So what we've decided to do is to go back to the start, to look at all the data we have, and to train, again, from Bayesian models, from essentially modeling assumptions, what it is that we could see from the data then, that we can now see from wearables that have, I don't know, an order of magnitude of the fidelity we could see back then. And it turns out that actually when you do that, when you scrap the models that you've seen, and the GPUs that you were using then are now superseded by several generations, what you see when you accept that the algorithms have an ethical, a philosophical challenge, is really much more interesting than what we could see before we challenged them ethically. And I think if you look at what people like DeepMind or even Elon Musk, when he talks about the ethics of AI, that's what they're getting at. I hope that this is what they're getting at. It's not the fact that AI could threaten the human condition. I don't think it can. It's designed by us. We're already threatening enough to ourselves. It's not really going to evolve to be any more threatening than we already are. I think the real challenge is to put an ethical barrier that itself evolves with the algorithm, a curated form of AI that understands ethics at the machine learning level. Thank you.